Good morning. I am Federica Filippini from Politecnico di Milano, and I will present you the ANDREAS framework, developed in the context of energy reduction strategies for artificial intelligence loads. Today's data centers have a growing set of quality of service requirements and very stringent environmental limits. This slide shows how much water a data center requires, at least as an order of magnitude, and which is the installed power in a data center facility. The forecast shows that the increase in installed power will go on year after year. We can say that the largest chunk of power consumption goes in the IT equipment, while another quarter is devoted to cooling systems. The drivers for innovations are requiring larger and larger datasets for training. The size of workloads is constantly increasing, asking for more and more computational power, bandwidth, and disk usage. This holds for both image processing tasks, for instance, and natural language processing tasks. NLP models, in particular, are constantly increasing in size in order to improve performance. A study on NLP models developed in 2019 highlighted how training a large-size model of about 1.5 billion parameters requires almost 300,000 kilograms in CO2 emissions. If we consider that deep learning always follows a trial-and-error approach, we can easily imagine how these numbers can grow. An average-size model can be trained almost 5,000 different times over 6 months, requiring more or less 27 years of GPU time and overall more than 35,000 kilograms in CO2 emissions. As a comparison, you can consider that the average American has been estimated to consume more or less 16,000 kilograms over 1 year. This was 2019. And what about now? One of the last released models for NLP, which is called GPT-3, has 175 billion parameters. I let you imagine how much CO2 emissions these can require for training. ANDREAS, which stands for Artificial Intelligence Training Scheduler for Accelerated Clusters, is designed to meet two specific market needs. First of all, the efficient use of high-value computational resources, which are, for instance, GPUs, that are commonly used to support deep learning training tasks. Second, the reduction of energy consumption, which can be called energy to solution. ANDREAS offers advanced scheduling solutions optimizing deep learning training runtime performance and their energy consumption in accelerated GPU clusters. Specifically, ANDREAS enables operators and data centers to keep the power consumption under control while optimizing the workloads. And it helps cloud end users to minimize the cost of resource usage in the cloud. ANDREAS have been supported by the TetraMax project within the technology transfer experiments. The three partners involved in the development are Politecnico di Milano, 7Bulls, and E4 Computer Engineering. The goal of ANDREAS is twofold. A user or a data center lives in these two dimensions, training time and cost. There are things that are feasible at all costs. However, usually there are two major constraints: a deadline which jobs should meet and a budget constraint. These are the dimensions where ANDREAS is working. It makes sure that users' jobs are completed within a budget constraint and a deadline constraint. ANDREAS have been developed as an integrated framework that supports the entire AI model training, including collecting profiling data for the given jobs and optimizing their execution. The framework includes two components: a job scheduler that receives job submissions and orchestrates their deployment, and a job optimizer that identifies the best job placement based on the description of jobs characteristics and available resources. These two communicate with each other and with the users through a REST-based API integrated with a SLURM scheduler. This is the structure of the optimization process. Given the queue of submitted jobs, their estimated execution times collected through profiling, and a description of the system with all the available resources, The job optimizer selects which jobs should be executed and on which type and number of GPUs. This process occurs periodically and every time a new job is submitted or a running job is completed. If resources are not enough to run all jobs concurrently, some of them can be preempted and their execution is therefore postponed. The optimizer exploits two different algorithms. First of all, a greedy algorithm that builds a schedule by assigning resources first to jobs closer to the deadlines in order to minimize the violations. The optimizer always tries to execute jobs on the cheapest available configuration. Second, the randomized greedy algorithm is built on top of the former, randomizing all decision points. Finally, the solution with minimum total cost is selected. We have evaluated ANDREAS considering heterogeneous neural networks implemented in TensorFlow 2.0. We have simulated different scenarios with a number of nodes going from 10 to 100 and jobs inter-arrival times generated according to datacenter loads. We have compared the results with first principle methods as first in, first out or earliest deadline first. As you can see in these four plots, we have evaluated both the energy cost and the total cost, which includes penalties for deadline violations. You can see that the randomized greedy method guarantees a reduction in all the considered scenarios. In particular, the energy cost reduction is between 5 and 10% on average, while the total cost reduction stays between 30 and 62%. This is due to the fact that ANDREAS optimizer guarantees a more efficient schedule that minimizes also deadline violations. These two plots show the average time required by the job optimizer to provide a solution. Even if you can see this time is higher than those required by the first principle methods, it remains still below 0.1 second in all the considered scenarios. Of course, this is considerably lower than the reconfiguration time of any system. Other than with simulations, we have evaluated our results on Armeda, which is a test and development cluster located at E4 premises. It is an 8-node cluster, and the characteristics of the 4 Armeda nodes we have considered are listed in the table below. You see that they have either 1 or 2 GPUs of heterogeneous types. Here you can see on the left the trace of jobs execution on Armeda, and on the right the plot of the total power consumed by Armeda nodes during the execution. This scenario proves the feasibility of ANDREAS framework, since the deviation between real and predicted costs is of about 12%. Now I will show you a demo of how the ANDREAS framework is used, going from job submissions and profiling up to the optimization and the deployment of such jobs, in a simplified scenario which has been designed for demonstration purposes. This demo has been recorded by Maciek Riedel from 7bulls, who is the leading developer of the job manager described before.
Hello, my name is Maciek. I'm a Java developer at 7bulls.com, and today I will show you a short presentation on ANDREAS platform. As you can see, I'm already logged into ANDREAS FE, which is a control unit of Armeda cluster. And inside ANDREAS directory, I would launch initialize launching script, which is quite easy to use. And this script would prepare our environment, would start most crucial components of the application, which is Jobs Manager and the optimizer, as well as the database. As it takes few seconds to start the application, I will show you that I already have prepared working directories for our training jobs, as well as uploading necessary scripts. I will show you one of such scripts. And as you can see, this is a Python. Python script using TensorFlow and GPU to train model. In this situation, it is LSTM network. And what is important to say, also added few things required by ANDREAS platform, which is, to be more precisely and most importantly, here saving the model after each epoch. So after each epoch, this script would need to save the model to the working directory, and it will be visible there. And because of that, ANDREAS platform will be able to scan the progress of the training. Okay, the application, the ANDREAS platform the application has already started. I would then switch to Postman program that enables us to send JSON messages. And then I have before submitting of the jobs, I need to set up the configuration of the system. We need to inform ANDREAS project about the valid nodes, and as you can see, I will send such JSON to ANDREAS. Which is important that I need to also specify if those nodes are just for training or just for profiling. We can always switch it later, but in this configuration, I would set that Armeda 6, which has 2 GPUs, would be specified only for profiling. I would send such configuration. As you can see, it has been processed. And ANDREAS project is connecting to those nodes to check their states. Then I can submit 8 jobs. And as you can see, I also needed to specify. How many epochs this such profiling would take. In this situation, I specified that each job would require 8 epochs for profiling, and as such data would be sufficient for the optimizer to determine the optimal assignment. I also had to specify the details of the paths to the working directories that I mentioned before, as well as the scripts that I have shown you already. Can switch back to. Okay, as you can see, the submissions are being processed, and ANDREAS would now communicate to the optimizer to assign jobs for profiling, and with on profiling nodes. And then with such profiling data, we would be able to submit jobs for the real training, which I will show you after a short break, as this profiling data takes time. Okay, we are back. The profiling has been finished. Almost immediately, we can go back to Postman and submit our jobs. We need to start with setting the configuration exactly as it was before. We just specify now that all the nodes are for running. Then we put false everywhere. And as you can see, quite fast, Jobs Optimizer sends all of this profiling data and the current state of the system and all of the jobs to the optimizer, and almost immediately we receive the answer where to put all of those jobs with the optimal solution. When the message is from the optimizer is received, we start those containers, and as you can see, the details here. We successfully started container for job 118 with the GPUs on Armeda 6. We can verify it on Armeda 6 if those GPUs are indeed in use. And as you can see, we have a process, this same process that is using two GPUs on Armeda 6. So current assignment is that one process is using 2 GPUs, and 3 other jobs are using Armeda 457, and the other jobs are waiting for them to start if the optimizer decides to assign them to nodes.
As a conclusion, which kind of applications can benefit from exploiting the ANDREAS tool? For sure, all services related to mobility and traffic, but also related to finance or weather forecasting or personalized healthcare. In general, all deep learning applications which require an expensive training phase can benefit from exploiting the ANDREAS tool for their deployment. Future developments of this tool may include the support to disaggregated hardware resources. Here you can find some pointers and references used in this presentation. Here you can find some pointers and references used in this presentation. Thank you for your attention.